So focus today is going to be on solving those exponential growth or decay equations for variables other than time. All right. So we started out solving for time. Now we're going to look at, well, what if we know the time and we're trying to work back and find out what rate we need or what principal we need to invest to end up with a certain amount of money. Okay. So to get started, we reviewed. One sec. All right, so our first review question. So the population of Allentown, Pennsylvania was 5,000 in the year 1900 and has steadily grown by 3.17% every year since. The first question just says, give me a generic equation that represents this growth. Okay, so total amount equals what? Equals what? In this case, what's our starting amount? 5,000. Okay, what's happening to it? Growing, decaying, what's happening? It's growing. How much? 3.17% we would write as what? 0.0317. All right. And it's happening every year for 2 years. Okay. So that's your generic formula for this specific question. Then in part B, it says how many people lived in Allentown in the year 2008? We'll go back to when did it start? In 1900. 2008 is how many years later? Okay, so you're going to put that in for time, 108. Okay, so 5,000 times 1.0317 to the 108th power. What do we get for a total? $145. Okay, so about 145,000 people by that time. Part C says, when would the population reach 150,000? Well, we know it took 108 years to get up to 145,000, right? So 150,000 is going to be a little bit more than what we've got. Yes? How do we work backwards? We want the population to be 150,000. We start with 5,000. We're trying to find time. How long does it take for that to happen? What do we do first? Okay, 150,000 divided by 5,000 is what? 150 divided by 5? 30. Okay, so we have 30 equals 1.0317 to the t power. And how do we find t? What? We do need logs. Okay, so let's take the log of both sides. The log of 30 equals the log of 1.0317 to the t power. Powers move in front, and then can we divide this log over? So we're going to end up with the log of 30 divided by the log of 1.0317. What does it come out to be? So about 109 years? Okay. All right, question 2 says an investment is made at 7% compounded continuously. Right there, what do you got to use? PERT, right? As soon as they say compounded continuously, you have to go to that method. It says, how long does it take for your investment to triple? Now, did they tell me how much I put in? No. Does it matter? No. Because if I say that I invest a certain amount and I want it to triple, I'm going to have 3 times that as my final answer. Yes? Our rate was 7%, so 0.07, and we're looking for time. And my first step is going to be to divide that principal over to the other side. But what's 3p divided by p? 3. So again, it doesn't really matter what the starting amount was if we're looking for it to triple or quadruple, things like that. So we really have 3 equals e to the 0.07t. We need logs again, but what kind of log should we use? Why? Because there's an e in it. All right, if I take the natural log of both sides, what happens on the right-hand side? The natural log of e to a power. Yep, we just get the power. All right, so with your calculators, natural log of 3, we need to divide that answer by 0.07. What do we get? How many years is it going to take? Questions on any of those? Look back at question C from the first one we just did. It said, when will the population hit that? We said it's going to take 109 years, and we started in 1900. So in what year would we hit that population? Okay. So we do need to watch carefully. When it says when, they're looking for a specific year, a time. When it says how long, just the number of years it's going to take. Okay. All right. So the new questions. We are looking for other things, like maybe we need the starting principal, or maybe we need to know what rate is needed. In this first one, it says, at what annual interest rate would 4,000 grow to be 5,500 if it was compounded quarterly for 6 years? Okay, I'm going to pause the video for a minute. I want you guys to write out what you know, fill into your formula the pieces that we already know. Okay, so it does say it is compounded quarterly, which means we have to go to that compounding interest formula where there's an n in the formula. Okay, so a equals p times 1 plus r divided by n to the nt power. And what pieces do we know? Do we know a? A is what? Okay, 5,500. Somebody else? P? Thank you. Do we know r? Okay. Do we know n? What's n? Compounded quarterly would be 4? 4 times a year? All right. And then here we have 4 times 6 for 6 years. Okay. So what can we do to simplify this? Yep, we can divide the 4,000 over. Okay, so take your calculators. What's 5,500 divided by 4,000? Do we have a decimal for it? 1.375. Okay. Now, can we simplify what's in parentheses? No, without knowing r, we can't put that together. How do we undo, because we're trying to get what's in parentheses by itself now, right, to figure out what r is? How can we undo a 24th power? Yes. If we take the 24th root on both sides, it'll cancel this on the right-hand side, and we just have 1 plus r divided by 4. On this side, we're going to have the 24th root of 1.375. So go ahead with your calculators. Find the 24th root. So put in your 24, go into your math. There should be a generic root symbol in there. Anybody got it? 1.013. What's the next decimal after the 3? Another 3? Another 3 and then a 5? So we'll go 4. Okay. what would we do next? Subtract the 1, which gives us 0.0134, and then times it by 4. Okay, so take your decimal. And now I've put a rounded answer up here, right? You should still have that big long decimal in your calculator. You should be able to subtract 1 from it, times it by 4, and just give me a final answer then, without rounding it at each step. Anybody else get that? Yes? Now, we are solving for an interest rate, right? And those are usually given as percents. So if you're seeing 0.0534, what would we put down as the interest rate? Yeah. Our final answer would be 5.34%. Okay? We good with that one? All right. Question 2. Your grandpa wants you to grow up to be a millionaire someday. He wants to put away some money when you are born to help you reach that goal. How long does $10,000 have to be put in an account earning 9.4% compounded annually to reach that goal of being a millionaire? Okay, so compounded annually, what would N be? 1. So do we really need to put it in our formula? Okay, so we're going back to this one, where we don't have to worry about N. All right, how much do we want for a final? He wants us to be millionaires. How many zeros are on a million? Okay. We start with 10,000 being invested. We're earning 9.4%. So what's going to go in parentheses? 1.094. And we are looking for time, yes? So first step, we can divide the 10,000 over, which basically means we're just taking off 4 zeros. Okay, so we want 100 equals 1.094 to the t power. Then what do we do? Logs, yep. So the log of 100 equals the log of 1.094 to the t power. Powers move in front. So we've got the log of 100 equals t times the log of 1.094, and then we'll divide that log piece over. So with your calculators, log of 100, what is log of 100? It is 2, right? 10 squared? Okay, so we could just put a 2 in there, divided by the log of 1.094. So how long does it take? $51.3 years. Anybody getting that? Okay, so if he puts this in when you're born, 51 years later, he gives it to you, you're a millionaire. Yes? Okay. Part B says, how much has to be put away at that 9.4% so that you get there by the time you're 65? So again, he's doing this when you're born. So if we want to get our money in 51.3 years, he had to put in $10,000, right? If we can wait 65 years, he doesn't have to put in quite as much. Okay, so let's work backwards and figure out what he would need to put in. We still want to be a millionaire. We don't know how much we're investing. Okay, we are getting that same 9.4% annual interest. But we know now that we can leave it in there for 65 years. Okay, we're not going to collect it till we retire. Can we type in our calculators 1.094 to the 65th power? Can we get a number for that? Yes? And then can we just divide it over? Okay. So we're really looking at taking 1 million and dividing it by 1.094 raised to the 65th power. Go ahead and figure that out. Okay, so think about that. He had to put in $10,000 if we wanted our million when we turned 51. He only has to put in a little under 3,000 if we can wait till we're 65. Okay, it has enough time to grow. Part C, what rate does your investment account need to average if your grandpa only had $1,500 to put away? So we're still going to assume we want this at 65, but now we don't know our rate. I'm going to pause the video and let you guys try this one on your own. Check with the people at your tables. Okay, so we are still looking to become a millionaire. Try that again. He only has $1,500 to put away this time, but we're going to be patient and wait till we're 65. So we know our rate has to be more than what? It's got to be more than the 9.4, right? Because at 9.4%, we needed to invest $2,900. We only have $1,500, so we're going to have a higher interest rate, all right, to make it work. Dividing this over gives us what number? Okay, how do we undo a 65th power? Take a 65th root. So you took the 65th root of this, right? And then you subtracted 1 from that answer. And you got R to be what? Came out to be 0.105 something, right? So 10.5%. Okay, so we'd have to have a more aggressive interest rate, all right? Maybe riskier funds, but over 65 years, it should balance it out okay. All right, our last question. It says, what growth rate would Elk River have to average so there are 100,000 residents in the year 2100? All right, it says, under the following compounding scenarios, annually and continuously. So think about the two equations that we would be using here. What would we need to know? Yes, we'd have to know a population. And you know, they do the census every 10 years, right? So we are going to base this off of the 2010 values. And it said Elk River's population was 22,974 in 2010. All right, and we want it to end up being 100,000? Okay, so what are we trying to find? A growth rate. We're looking for R, right? This one, it says we're assuming it's an annual growth rate. And we want this to be the year 2100. Well, keep in mind, our starting population is the value in 2010, right? So how many years later would be 2100? Okay, so we're going to put 90 in. So we're going to solve it exactly the way we just did the previous question. We're going to divide out the 22,974. Then we're going to take a root and subtract 1. Yes? So we are going to be taking the 90th root of whatever we get when we take 100,000 divided by 22,974. Yes? And then at the very end, we're going to subtract 1 from that. kind of growth rate do we need? What'd you guys get? Brennan? Okay. How would it be different if it was continuous growth? Now we switch to which formula? Okay. So we still want 100,000. We start with 22,974. We do not know our rate, but we know our time is 90. So our power is 90T. Sorry, 90R. Yes? Okay. Can you still divide the 22,974 over? Okay. So on your calculators, get that decimal. 100,000 divided by 22,974. Then what are you going to have to do to it? Okay, let's take the natural log of that answer. So whatever you had here, take the natural log of that answer, and then when you find that, divide by 90. What do we get? When you did this, you should have had 1.4709 equals 90R. Dividing that by 90 gave you what? All right, so about a 1.63% growth rate. Questions on that? We good? All right, so you have a blue worksheet for tonight.